Welcome everybody to Happy Maths Hour. Toni, what's this session about? It's my favourite subject.
It's fractals, but it's not all about fractals. There's a lot more than, but we're probably gonna do some more on fractals next week. There's so much we might do, but this is just a little bit about fractals. In particular, it's about something called the Sierpinski Gasket, or well, we'll do it in 2 and 3 dimensions. So without more ado, it's Fractals 1.
This is the first of 2, possibly 3 fractals sessions.
So what is a fractal? Well, a very simple definition is to say it's a shape, could be a curve, that's made up of infinitely many copies of itself. And the emphasis there is on the infinitely many. The copies may get smaller and smaller so that the shape doesn't grow to be unmanageably large. And we'll see lots of examples of fractals, and here are some. Now, these are some that occur in nature. The green and white one, and the top center, believe it or not, is taken from space, and it's a picture of rivers and the snow. And the rivers have sort of melted the snow, so you see the green banks of the rivers. But what you see is the main river, the big branch, as it were, and then smaller and smaller branches and tributaries of those. And that is a typical fractal structure. And then below it, you see the lightning. Again, as with the tree below, you've got the main stem and then smaller branches and smaller ones, those twigs in the tree and smaller ones. And that is a typical fractal structure. As indeed.
What I love about the tree is that you've got the fractal structure above ground, but of course you've also got the fractal structure below ground. The roots form a fractal structure as well.
The roots, yes. Not so easy to have a photograph of that, though. And then the clouds are again fractal.
Well, that's less. Yeah, that kind of needs some explaining. I would have never thought of the clouds as fractals. So why are the clouds fractals, Toni?
Well, there's a bit like the coastline below. You've got smaller clouds and smaller ones, little fragments of clouds scattered around. So the sky itself is bigger clouds and smaller clouds and smaller clouds, not necessarily identical shapes.
I can see like a big cloud. If you actually start looking into detail, you can actually see smaller clouds make up as you say, the bigger clouds as small structures. But again, the coastline, I was very surprised when you said the coastline is a fractal.
Well, as you go around a coast of any coast, you see bays, quite big bays sometimes, like False Bay, which is where I used to live in South Africa, and Caroline's father lives. And that's a very big bay with lots of little towns around the bay. And then inside the bay, there are smaller bays. And inside those cliffy edge to the coastline, you see even smaller and smaller little chinks in the rocks as well.
Okay, so you've got the beaches. The beaches are mini bays within the bay, but then, as you say, with the rocky edges, you've actually then got lots and lots of much smaller
little crevices,
indentations, indentations that then make up, and then within that you've got the rocks, the individual rocks that make up. It's I've never thought about it. I would have certainly never thought of clouds and coastline.
Well, one of the,
it's a lovely idea that the coastline's made up of fractals.
One of the the puzzling questions about the coastline is how long is it? And you could imagine that, okay, if you were flying from one point to another point along the coast, you might fly through a bird, you might fly absolutely straight, but that's not the length of the coastline. And so if you imagine following the edge of the coastline, going into every crevice and cranny and beach and little bay, and keeping and you would get a very much longer coastline, and you might find smaller bays that you didn't go in, so you should go into those as well. So what you have got is a very long coastline when you when you add it up.
So there's a difference between the way the bird flies following the coastline, and if you actually followed literally every nook and every cranny, it would take a lot longer to cover the whole coastline. And that's even if we're humans, we're taking a step, we're bypassing a lot of the little itty bitty nooks and crannies with in the rocky areas.
So if you were a little, I don't know, a little sea creature of some, sand creature. An ant.
Sand ant.
How long, if you followed the edge, how long would your path be? And we've got other things like broccoli, which you can imagine if you break a piece off the broccoli, it looks like the big bunch of broccoli. And then you can break another little bit off that. And inside ourselves, our lungs have got pockets, and of those pockets, smaller pockets and smaller pockets. Our lungs are fractal. And so is the system where our blood flows, called the vascular system of veins and arteries, because we've got big arteries and we've got smaller blood vessels that come off them. So we're going to look this afternoon and talk about and show you some of our adventures with Sierpinski. There was I should have put something about Sierpinski in here.
Oh, yeah, I've had to learn how to say his name because I do go to Poland and I've got a few Polish maths teachers, and it's like they think it's hilarious when I call him Wacław Sierpinski, and the best I can do is Wacław Sierpinski. I hope I've got it more or less right. I'm sure they'll correct me if I've done it wrong.
He was a Polish mathematician, like many other people in his time, interested in fractals, and he invented this pattern. And what I love about this pattern is that you've got so many equilateral triangles and so many questions you can ask about it. We'll come to the questions in a
yeah, I mean, this really goes, because I facilitate this with nursery children on one level, and it can go all the way up, all the way through the education system with the spiral learning idea that you just keep adding more onto the same topic all the way up to, well, degree. I mean, past degree, and mathematicians still study it as research. So it's very rich.
We've got 4 stages, or stage 0, 1, 2, 3, 4 there. But if it were a real fractal we were showing you, there'd be infinitely many stages. So we're just showing you a pattern that keeps repeating itself. I think you can see that here. So you can imagine hollowing out those inverted triangles, the ones that are point down. So you take the midpoints of the edge and you hollow out the middle. And then with the 3 black triangles that are in stage 1, you do the same again. You take the midpoints of the edge and you hollow out the middle. And then you've got 9 black triangles and you do it again. And you've got 3 times as many now, so there are 27. And again, and again, and again. So you can make the fractal. There's a lot of white space there, isn't there, in that fractal?
There's a lot of white space. It's, yeah.
And you can ask a question like, how many triangles at each stage? Which I was answering as I talked about that. How many of the black triangles, how many of the white triangles at each stage? But you can also ask question like, what area do the triangles cover at each stage? And you see, you've got to add up the areas of all the triangles, and there's infinitely many of them. So that's the question.
But is that sounds a bit like it's counterintuitive, because the more triangles there are, the less area they cover.
Well,
and yet there's
we're talking about the fractal would have infinitely many stages, as you see them, and so we can give a sequence. There's 3 black triangles in stage 1. There's 9 in stage 2. There's 27 in stage 3. There's 81 in stage 4. And in the next stage, there's 3 times that many. So there's 243. So when we add up the areas, we have got to say how many triangles there are for each stage, how many black, we're doing it with black triangles, say how many of them there are, what's the area of each one, and that term will be that number of triangles times the area of each one. So you're going to have a progression or a sequence there. And that's a question you could ask to 16, 17, 18-year-olds, expect them to be able to do it. But you could ask the younger learners to describe what they see and talk about the patterns and count the triangles.
And draw the triangles.
Draw it. Yeah. Let's carry on with drawing.
Ooh.
Now,
exciting.
So what we've said is fractals contain copies of themselves at a smaller scale, and you can see that with these black and white triangles that we've shown here. And as we've just described, you can join the midpoints of the edges of the black triangles and remove the inverted triangles at each stage, leaving a white space. But there's another way to look at it. You can think about the fact that you might reduce the area of the triangle so the lengths of the edges are halved, and make 2 copies and arrange the 3 triangles with 2 side by side and 1 on top. And then reduce it again. So it's the edges are half the length. And you make more copies and you repeat the stage 1, 3 of them to make stage 2. And 3 stage 2s make stage 3, but in my picture, they're reduced in size. Or we can make them grow, and in a minute, we'll see them growing bigger. So our fractal can grow bigger, or it can scrunch in on itself and grow smaller. Nice idea. Now, by making the Sierpinski triangles and describing what they see and noticing and talking about the geometrical properties, the young learners will be able to develop visualization and language skills. And that's really important, that they can notice what they see, they can describe what they see, and they can observe the pattern. Maps is full of patterns.
And for this, that they don't have to have a lot of prior knowledge. They can just, as long as they can count and they can say the word triangle, they can really describe this in a lot of detail in their own way.
Yes, indeed. Yeah, and different children may describe it in slightly different ways, as we've been doing now. But essentially, they have valid observations to make. And older learners can investigate number patterns and spot similar triangles and work out scale factors. They can investigate areas, numbers of triangles in the patterns, and even some infinite geometric series. So there's a lot of potential here for learning the standard mathematics that you have to learn in any school curriculum. Now then, we're going to show building one of these triangles in a slightly different way. So if you watch now, you will see that these triangles are building up in the way I described, but now we're not shrinking them. We're taking lots of copies of the same size and we're adding them in. So we have started with 27 stage 2 triangles.
The stage 0 is just one triangle, you can see. 3 smaller triangles of half the length, that's a stage 1. So effectively using 3 triangles to make a stage 1. The stage 2 is you're making 3 stage 1s together to make a stage 2. So if you look at the stage 2 there, that is the building block that Toni is using.
You've got 3 of each given stage, you make 3 of them to make the next stage. 3 stage 2s to make a stage 3, and 3 stage 3s to make a stage 4,
etc.
What I like to do with a group is to say, here's your copy, and it could be a stage 2 like this, or it could be a stage 3. Color it in, and then we'll stick your triangles, the ones you've colored, on a backing sheet, and we'll make a poster. And if we have a big enough space, we could go even further than this. This is a stage 5, but if we had enough space, we can use 3 of these to make a stage 6. And
I like to get the group to visualize what would happen if we pointed this towards the moon. How many times would we have to, how many stages would it take? We're starting at, let's say, a 1 meter. Let's say the edge length of the first one is 1 meter. How many, at what stage would we actually reach the moon? And that's a nice, fun little activity that gets them thinking.
Also, what you've got to imagine is this fractal could have, not as you see it now in that picture, but it could have smaller and smaller triangles within the ones you see. And it could go on shrinking down and down as well. You can have infinitely many iterations, is the word we use in mathematics to mean you just repeat the same process over and over again. And in your imagination, you can imagine doing this infinitely many times. So that's the stage 2 triangle, the little one up at the right there that we've used. And we've used 27 of them to make a stage 5. And we'd need 3 times 27, 81 of them to make a stage 6, and 243 to make a stage 7, and so it would go on. And now we want to jump from 2 dimensions to 3, and we've got a very short video. Now, can you see there that what the group have built are not just triangles, although you see lots of triangles in the picture. It's all made of balloons, and so they're sagging a little bit, but it's pretty clear that what you've got there is the same sort of structure as we've just been talking about with the triangles, but they're made with tetrahedra. Let's watch it once more. It's very short. And now, fantastic fractals, aren't they fantastic? So let's compare pyramids, because we use the one word, and we can have a pyramid with a triangular base, as you saw with the balloons there, or with a square base, or with any other polygon, actually. It doesn't have to be a triangle or a square base. But here are some real life tetrahedra and pyramids. We've got a pyramid tea bag, the pyramids in Gaza, the art gallery, the pyramid at the Louvre in Paris. What's the same about these shapes and what's different? Well,
another question is, what's the same about all pyramids? No matter what the shape of the base is, what is the common factor?
Well, the sloping edges are all going to be triangles, and the base can be any polygon. And the triangles very often are equilateral, but they don't have to be. They're usually symmetrical in the sense that they're usually isosceles triangles. Again, they don't have to be. Now here you see the balloons again, and here the colors make it quite, the construction quite clear, how the tetrahedra are made with 6 balloons, 6 edges with 6 balloons, and how you have 4 of them to make the bigger tetrahedra at the next stage. There's a question that is quite a challenging question if you've not looked at it before, is what is the shape inside the big tetrahedron between those balloons? What Caroline and I were talking about this, and she thought it was perhaps easier to see with the shape, the pyramid on the left, that's made with newspaper sticks.
I've got my one that's made out of solid tetrahedra here that might be easier to see, and with the visualizer. You can see the shape inside there if I move it around. Now, if I put it sitting the way the one is on the bottom left, but I've actually got. Do we want to reveal the shape? Because I can, because I've got it here, Toni.
Oh, why not, Caroline?
So I'm going to open this up, and I'm going to put this shape. Let me raise that up a little bit more. I'm going to put this shape here in the middle so that you can see it fits. Now this is a solid tetrahedron. It's completely solid, and the shape of the gap in the middle.
Caroline, when you were going to put that in, it looked almost too big to go in.
Yes.
It's sort of counterintuitive, but it does. It fits in neatly there, and just exactly fills that space.
It does, and it is actually geometrically correct. It's made up. This shape here is made up of 2 of these pyramids, but put together differently with different angles. So all the edges are exactly the same, but can you see the shape?
So it's got 8 edges. So it's an octahedron.
And if you look at it straight above, you can see 1, 2, 3, 4. You've got a square, which is one of the planes of symmetry. And if I turn it the other way up, you can see you've got 1, 2, 3, 4 identical top and bottom, so you can see the symmetry, and it's really easy to work out how many faces it's got. And yes, its ancient Greek name, which is the mathematical name, is Octahedron, which means 8 faces.
And if you look at the colored balloons there, at each vertex you can see in one vertex you can see 2 yellow and 2 blue balloons for your 4 edges. At another vertex, you can see 2 blue and 2 pink balloons. At another vertex, you can see a pair of 2 balloons of one color and 2 balloons of another color, giving you the edge of your octahedron at the 6 different vertices.
And that's, and you say, so you've got 4 triangles that are tricolor, and 4 triangles that are monochromatic, that are one color. It's a bit hard to visualize there. It's easier if you've got a structure right in front of you. You can literally manipulate.
I thought your paper one was beautiful, Caroline.
I thought that would do the trick.
Yes, really good. Okay, now then, we're going to show you, Caroline's going to show you a video of this occasion. It was quite a few years ago now, and it was in a shopping mall in Cambridge, and it was part of the Science Week celebration. And we had a big team there making this Sierpinski Tetrahedron. And it was great fun. It lasted a whole day, didn't it, Caroline? We didn't finish making it until quite late in the afternoon. And then we measured it.
It took us 24 hours, Tony. You weren't there for the beginning. We arrived at 5 p.m. the day before, 5 in the afternoon.
We started
inflating. We did have a bit of a sleep. We did, but we started it basically from start to finish. It was 24 hours with maybe 4 or 5 hours sleep. So it took a while, and it was an attempt at getting a Guinness World Record for the world's largest Sierpinski tetrahedron made from modeling balloons. We didn't get it. It wasn't good enough. You can see it's a little bit wobbly there, and they weren't satisfied with that, and we didn't have a surveyor measuring it. Two professors from Cambridge University weren't good enough. It had to be a surveyor.
And yes, it was a really ambitious project, and people very much enjoyed it. Well, Caroline's going to show you a video. It's a time-lapse video of the day as we assembled it. It's so clever. You get the fourth piece on top, because it's so, you see the people standing there. It's so high above everyone's heads. It's really clever the way you get that last piece. You raise it up and get it on top.
We do this as a regular workshop using much larger tetrahedra, and so it only takes a few minutes to assemble it. It takes about 3 hours to get it ready, and then it only takes a few minutes to assemble it and make it as big as that. And throughout that day and throughout every day, every time we do it, people come up and, how are you going to lift it up? How are you going to put it all together? How are you going to do it? And we won't tell. It's a secret. We won't tell. And then we tell them to come back at the time that we're going to raise it. And they come back, and we always have a big crowd, and it's raised up, and we always get a, oh, from everybody. It's very
exciting. Yes.
And then when it's done, we always get a cheer. It is a lovely project, and we get whole families helping out, and it's a great family workshop.
And the reason it takes such a long time is you start with these long balloons, and you have to split the balloons into shorter lengths, don't you, Caroline, to make the twist them and make the each small tetrahedron with the smaller balloons.
Yeah, and they have to be very accurate to get the Guinness World Record attempt as well. And so we did our best, but things did go wrong on that occasion. We finally got our world record by making a much smaller balloon. If you can see, Simon, he's got wearing an orange outfit, and he's got his arms up in the air like this. The what's directly behind him, up to the top, just above his head, that would be the size of 1. So it was a stage 3. It's only a stage 3. No, it was correction. It wasn't a stage 3, but it was that size. It was 2.64 meters long in edge length, and it had to be that accurate. It had to be within 2 centimeters. All of the tetrahedra all of the edges had to be within 2 centimeters of each other and of the length. So that's what it took. That's what it took to get to the world record, and this one just wasn't accurate enough. And even if we had a surveyor measuring it instead of 2 maths professors from Cambridge University, then I'm not sure that we'd have got it, because they are very finicky about the quality.
The thing is that because we were so ambitious and made it so tall, the balloons sagged under their own weight. They didn't have enough rigidity, and by making a smaller one, although it wasn't so impressive in many ways, the actual balloon stood up and you got the better tetrahedron shape. So
well, next year we're making another one using 16 of the ones that we made. So we've got a big logistical project next year to break our own world record by making 16 of the ones that we made already, which is going to come up in a little bit.
That would be a big challenge. So all day, my husband and I, you see us on the left-hand end of that row of people. We had a stall and we got toothpicks and blue tack and pieces of card, and children and families came along all day. We were busy making their own Sierpinski tetrahedra with the toothpicks for the edges, and at the vertices sticking the toothpicks into little blobs of blue tack. And they went away proudly carrying their piece of card with their Sierpinski tetrahedron on it, made of toothpicks.
And that was the stage one that they were making, wasn't it? It was 4 tetrahedra.
Yes. And how many of them actually got that home without it collapsing, I don't know. But of course, they could have always rebuilt it.
Yeah.
And then all day, as we've described, and you saw in the time-lapse video there, people were building this Sierpinski tetrahedron. And then at the end, of course, the end of the day, before the shops were all closed and people went home, we had to dismantle it. So families went home, each of them with their own balloon Sierpinski tetrahedron, and it wasn't hard to clear up, was it, Caroline?
It wasn't. No, we never have any balloons left. Even if there's one balloon left, somebody wants it. With the one that we do with the meter length tetrahedra, we don't have any problems. We tell people come back at 4, and there's lines and lines of people at 4, and they all want a section of this amazing structure. So it's a lovely workshop, whether it's the world record attempt or just the normal workshop. People love building it and they love taking their bit of it home.
And we can ask how many of the tiny tetrahedra are in each part, and how many in the whole structure, and what is the total length of all the balloons that are needed. There's lots of questions we can ask, and then given the edge length, what is the height? Because geometrically it should be a regular tetrahedron, and if it was regular, then what would the height be? You could do a scale drawing, in fact. You don't have to know any trigonometry. You can do all of that by scale drawing. So there's quite a lot of maths involved, and there's maths for all ages. I mean, the pictures we showed you of the pyramids was one of the ideas for younger children, but there's lots and lots of ideas for lessons with older children too that can follow on from this sort of exciting activity. And here you see another copy of that picture, but this was in our local newspaper. This balloon pyramid, which set a new record, and there you are. You've got the same picture. And
well, no, it didn't set. Well, we did set a record because nobody had done it before, but we didn't get into the book. When you can see the much smaller pyramid, you can see me standing up in my orange outfit. I'm nearly as tall. Well, it
wasn't nearly. I have to say, Caroline, it may have met the requirements, but it wasn't nearly as impressive, was it?
But it was useful. It was learning, always be learning, and always find, what am I learning from this? We witnessed what was required to measure it, because the lady in the photo with me there, you can just see it. She's just kind of a black shadow there, but it was Craig that measured it, the lovely gentleman in the picture that actually measured it. And they measured 3 edges, not 1, not 2, 3 edges, and they had to be within a certain
So
close enough so we know we have to do that, and we have to film up close that measuring happening, so we have a lot better idea how we can do it to make sure we get the next one.
Caroline, tell me again, because you did say, and I think you said you were going to do 16 of the one that you see in the book there. Is that right?
Yeah. That's 2.64 meters edge length. We're aiming for 2.5 meters edge length. And that is because we're working with a college in Norwich, and that's what they want to do. They want to make it basically go for the 8-meter edge length, the size that we made in Cambridge, but using 16 of those. Now, it took us 5 hours for 10 balloon artists, professional trained balloon artists, to build that. It took us 5 hours. So what I love about it is if they can make it happen, that'd be amazing, because it would be the students at the college that do, well, obviously it'll be supervised, but we would require catering. That's a project for they've got to then do all the maths around how much, when the food is required, how much food and all that. It's a project for the management team. So it's a project to manage. And there's training involved, so we can get the college students to help us with the training, to help coordinate it. The professionals, we'd be the consultants, but it's a huge project. So if they can actually manage it, it's a great project for training for these students to really get grips with a big project. And if they then get a Guinness World Record at the end of it, wow, what a fantastic activity for them.
But they'll have to be the small balloons like you used, and then 16 of those.
We're using, the small tetrahedra, but we're using the next balloon. The size of balloon that we used for that one are really skinny ones, and we're using the next size up and so they'll be very solid tetrahedra. There'll be very little space inside them, because we're making them quite small. There'll be 10 centimeter edge lengths, whereas those were 4 centimeter edge lengths that you see there, the orange one on the picture. And whereas these will be 10 centimeter edge lengths, but with much thicker balloons. So they'll be very, very solid. So they'll hold up well, and they'll be easier to make.
And I think what I see there is a Pooh Bear on the page of that book made of balloons.
No, that's not. That's actually was a world record that I also was a participant for. That is actually a mini Lego figure, although it's the standard one with the yellow skin, red top and blue trousers, the original one. That was 5 meters tall and 5 meters high, and it took us again also about 5 hours, maybe 8 hours to build that. And so I was very privileged to be on the team for that. That's how we got the 2 world records, because we spoke to the chap in the picture who's the editor-in-chief of the book, and he loved the idea, and we managed to get 2 world records out of it. But yeah, that's a mini Lego fig, but instead of being this big, it was 5 meters tall.
But Caroline, it was made, you mentioned Lego. Was it made in Lego or balloons?
No, it's balloons.
Yeah, well, I thought it was balloons. So.
But it's a Lego it's a balloon sculpture of a Lego minifig. Lego minifig is this big, whereas it was a huge model. We usually talk about smaller scale. You have a model car or a model airplane or a model something. Well, we made a model out of balloons, but it was 50 times the size of a Lego minifig.
I don't know. It still looks like a Pooh Bear to me.
It's a Lego minifig. It's definitely a Lego minifig. And that, if you want to look at that, that's the 2016 Guinness World Record book, which is the gold. The color is gold. So if you're to library or anything, you'll be able to see that. It's around page 90. So you can see the Lego minifig for yourselves. You can decide. You send us a message, say, well, is it a Lego minifig or is it Pooh Bear? You can let us know what you think.
But you've been involved, Caroline, with making other big balloon sculptures, haven't you?
I made a 30-foot octopus once. That was really cool.
That was wonderful. Yes, I saw a picture of that. Fantastic.
I made a 3-meter Happy Feet balloon sculpture. I love making giant balloon sculptures. It's one of my favorite things to do.
Brilliant. Absolutely. What fun. Yes. Yeah. Okay, so goodbye from us. Bye-bye, and we'll see you next week.
Bye-bye. Thank you.
For greater understanding and enjoyment of mathematics, the Maths Toys YouTube channel is brought to you by AIMSEC and the Aiming High website. In the description, you will find a link to our home learning guide for ages 4 to 18 and a teacher resource pack. If you find this video useful, there is a GoFundMe link in the description to donate to and support AIMSEC. The money goes to bursaries for professional development for teachers in disadvantaged communities around the world. Subscribe, comment and ding the notification bell to make sure you don't miss our latest activities.